Good day everyone. For today's video, I'll be discussing hydrostatic forces on plane surfaces. Let's take a look with this container filled with fluid. And we all know from Pascal's law, pressure is always equal with the same level of fluid. Therefore, if we take a look with the bottom of this tank, the pressure here is uniformly distributed. And if the pressure over a plane area is uniform, like in this case, the horizontal surface of the bottom of the tank filled with this liquid, the total hydrostatic force or the total pressure is given by force is equal to pressure times the area, where P is the uniform pressure and A is the area of the horizontal surface subjected with the pressure. Take note that we can only use this equation if the given plate or given surface is submerged in horizontal position. What if we encountered a inclined or vertical plane submerged in a liquid? How are we going to calculate the total hydrostatic force on that plane? So let's take a look with this liquid with free surface. And we try to submerge a plate at an angle theta with the horizontal axis. Let's say this is our y-axis and the x-axis is pointing toward us. As we try to rotate this about this y-axis, we can have this axis now. We can now see the face of this plate facing towards us. What we are going to do is to calculate total force acting on this surface. But we can't use the formula force equals to pressure times the area because the pressure now is not evenly distributed. As we all know, pressure increases with height changes. Therefore, to solve for the total force acting on this surface, we can only analyze a small differential A. Let's say that small area has a distance h below the surface, and let's measure this area y distance from the free surface along the y-axis. And also, this differential area experiences a differential force. If we try to add these differential forces along this area, we can now have the total force acting on this surface. To do that, let us use this equation, substituting the differential force with the force and this small area with this one, and from the principles of hydrostatic, to calculate the pressure any point below the free surface, it is just the unit weight times the height. Substituting that to this equation, we have this. And as we can see in this diagram, this theta is also equals to this theta because they are alternating angles. We can now relate h to y by trigonometric identities, giving us h is equal to y sine theta. Substituting this to this equation, we have this one. Integrating both sides, we have this one because gamma sine theta is constant. From calculus, this integral y dA is also equal to a multiplied to y bar, wherein a is the total surface area of the object, and y bar is the distance of the centroid of the object from a reference point. In our case, let's say this is the center of gravity or the centroid of the plate, and if we try to measure that along this y-axis, we have this y bar because our reference point is our free surface. Therefore, we can now substitute this one to this equation, and integrating the differential force, we have now this equation. And let's say the vertical distance from the centroid from the free surface is h bar. So we can relate now h bar, y bar, and theta, wherein h bar is y bar sine theta. Substituting that to this equation, we have now this formula. So this is now our formula in computing the total hydrostatic force in a inclined or vertical plane submerged in a liquid. We can also rewrite that into different equation. Take note that this unit weight h bar is just equal to the pressure at the center of gravity. Then we can substitute this pressure at the center of gravity at this unit weight h bar. So we have this equation. These two equations will help us to solve for the total hydrostatic force acting on the plane or inclined surface, where F is the total hydrostatic force acting normal to the plane in Newton, A is the area of the plane in meters squared, h bar is the vertical distance of the center of gravity from the liquid surface, Cg is the centroid of the plane. Take note that this force F is not located at the center of gravity. It could be found somewhere below at that point, wherein it should be acting directly at the center of pressure. To locate this center of pressure, let's say this distance is equal to yp. By Varignon's theorem, the moment of any force is equal to the algebraic sum of the moments of each component. In our case, we can express that in this equation. We already found the value of differential F, which is equal to this one, and also the total hydrostatic force acting on the surface, which is equal to this one. Substituting this to this equation, we have now this one. Let us remove the constant from the integral sign. We have this equation. And from statics, this integral y squared dA is the moment of inertia. In our case, this moment of inertia is about this point O. Therefore, we can now substitute this to this equation and cancel the same variable. Therefore, we have this equation. By transfer formula of moment of inertia, substituting now this equation to this one, we have this. Then solving for yp, we have this one. Simplifying further, we'll give this one. Let's say the distance between CG and CP along y-axis is E. And we can see that YP is equal to E plus Y. Therefore, we have this equation. Substituting this to this equation will give us this one. And then, we can now cancel this Y and will give us the formula of eccentricity, where E is the eccentricity measured from CG to CP along y-axis, IG is the centroidal moment of inertia, A is the area of the plane surface, y bar is the distance of the CP from the free surface along the axis of the plane surface. To further understand the concept, let us take a look with this problem number 1. A vertical rectangular plate 1 meter wide and 3 meter high is submerged in water with its top edge at the water surface. Find the total pressure acting on one side of the plate and its location from the bottom. Drawing the problem, we have this water with free surface and submerging a plate vertically with a height of 3 and width of 1. This plate now will experience a varying pressure wherein on its top is 0 and then a certain pressure at the bottom. To solve for the total pressure acting on this plate, we have this equation. Force is equal to gamma h bar A, wherein h bar is the distance of the centroid from the free surface, which is 1.5. Substituting that to our equation, we have 9.81 multiplied to 1.5 times the area, which is 3 times 1. We've used here 9.81 kilonewton per meter cube because this is a water and unit weight of water is this one. Force now will be equal to 44.145 kilonewton. Solving now for the value of E, which will lead us to solve for the location of this force. And the formula of E is equal to Ig over area multiplied to y bar. Take note that y bar is this one. From what we derived earlier, this is the distance from the center of gravity to the free surface along the plane. In this case, the plane is placed vertically. Therefore, y bar now will be equal also to h bar. Then solving now for the moment of inertia about the centroid, we have Ig equals to bh cubed over 12, wherein this equation is the moment of inertia of a rectangular object, wherein b here is the base of our object parallel to the water surface, and h is the height of our object. Substituting the values, we have this, and the moment of inertia of this object now is equal to 2.25 meter raised to 4. We can now substitute that to the equation of eccentricity. Therefore, we have 2.25 meter raised to 4 over 3 meter times 1 meter, which is the area of this object subjected with the pressure, and then multiply to 1.5, which is the y bar, that is also equal to h bar. Therefore, our E now is equal to 0.5 meter. Take note that this E is the distance between the CG and the center of pressure where the total hydrostatic force is located. What we are going to solve is the location of this force from the bottom. If we try to measure that, let's say that is x. Solving for that value, x is equal to 3 minus 1.5 minus E. Therefore, x now is equal to 1 meter. We can also solve these values using different approach, such as drawing its pressure diagram. As long as we know how to draw its pressure diagram, we can calculate the total hydrostatic force acting on that surface. In our case, the pressure acting on this surface is shaped like a triangular prism. If we will get the volume of this triangular prism, that is equivalent to total hydrostatic force acting on that surface. To do that, we need the magnitude at this point, which is equivalent to the magnitude of the pressure at that point. To solve that, we have this equation gamma h. Substituting, we have 9.81 times 3. Solving for the pressure will give us 29.430 kilopascal at this point. We can now solve for the volume of this pressure. From our solid geometry, the volume of this is equal to 1/2 times base, which is equal to our pressure, times height, times the width. That will give us the total force acting on this plate. Substituting now the given, we have 1/2 multiplied to 29.43 times 3 times 1. That will give us a force of 44.145 kilonewton, which is equal to what we've got from the previous solution. And to solve for the location of total hydrostatic force, which is located at the center of pressure, we can solve that using the centroid of the pressure diagram, because at this point, the total hydrostatic force is located. And from our geometry, the location of the centroid of a triangular prism is just 1/3 of this one. So that is 1/3 times 3 is equal to 1 meter, which is equal to the value we've solved from the previous solution. So it's up to you now what you're going to use. It's either the first solution or this solution. With that, let's jump with the second problem. A vertical triangular gate with top base horizontal and 1.5 meter wide is 3 meter high. It is submerged in an oil having specific gravity of 0.82 with its top base submerged to a depth of 2 meters. Determine the magnitude and the location of total hydrostatic pressure measured from the CG acting on one side of the gate. So we have an oil and we submerge a plate having its top base submerged, meaning the base of triangular gate should be on top and its base is equal to 1.5 meters and height of 3 meters. We're about to solve the total hydrostatic force acting on this surface. To solve that, we need the value of this h bar, wherein h bar is the distance from the center of gravity or CG from the oil surface. From our geometry, the distance of the centroid of this object is 1/3 from its base. Given that the top base is 2 meters from the oil surface, we have the h bar now, which is equal to 3. Solving now the total hydrostatic force will give us the unit weight, which is 9.81 times 0.82, which is the specific gravity of oil, multiplied to h bar, which is equal to 3, and then the area of this triangular gate, which is equal to 1/2 base times height. Therefore, force now is equal to 54.298 kilonewtons. And to solve for the location, total hydrostatic pressure, that is just equals to, wherein Ig is the moment of inertia with the centroidal axis over the area of the gate, multiplied to y bar. In this case, to solve for E, the moment of inertia with respect to centroidal axis of a triangular object is equal to bh cubed over 36, or 1.5 times 3 cubed over 36, wherein your B should be parallel to the oil surface. And then the area is still 1/2 the base and the height. Multiply to y bar, wherein your y bar is also equal to h bar. Therefore, we have this equation. Solving now for E will give us 0.167 meters. That's it for the first part of calculating total hydrostatic pressure on plane surfaces. Thank you for watching.